You think you know this one. Nuclear fusion. Hydrogen fuses into helium. Energy is released. Sun shines. You learned it in school. You've heard it 100 times, and it sounds complete. But I want to ask you something. That answer, does it actually tell you where the energy came from? Does it tell you why mass converts to energy? Does it tell you where the sun got the energy to start fusing in the first place? Because if you follow those questions honestly, all the way down, the answer reaches back before the sun existed, back to a collapsing cloud of gas, back to the Big Bang. And it ends somewhere that should genuinely unsettle you in the best possible way. I'm Paul Dirac. Let's think about this properly. The sun did not turn on like a match. That image of ignition, of something sparking to life, is wrong in a way that matters. About 4.6 billion years ago, a vast diffuse cloud of hydrogen and helium gas began to contract under its own gravity. Slowly at first, then faster. As the cloud collapsed, gravitational potential energy converted into kinetic energy. The particles fell inward, accelerated, collided harder and harder. The core temperature climbed. 100,000 degrees, 1,000,000, 10 million, 15 million Celsius. At that temperature and pressure, something new became possible. But here's what I want you to hold on to. The energy that heated the core to fusion temperatures didn't come from fusion. It came from falling. Gravity did the work. The sun's energy budget started with gravitational collapse, with a cloud of gas falling into itself, and fusion is what took over once the conditions were right. Gravity lit the fire. Fusion is what keeps it burning. So what does fusion actually do? Let's be precise here, because the common explanation glosses over the strangest part. 4 hydrogen nuclei, 4 protons, fuse through a series of steps into one helium-4 nucleus. If you weigh the helium nucleus and compare it to the 4 protons that went into it, the helium is lighter. Not by much, about 0.7% of the original mass is missing. And missing is the wrong word, because it didn't go anywhere invisible. It converted directly, completely, into energy, exactly as Einstein's equation demands, E equals mc squared. The missing mass multiplied by the speed of light squared gives you the energy released. The speed of light is a large number. Squared, it's enormous, which means even a tiny amount of mass produces a staggering amount of energy. The sun converts approximately 4 million tons of its own mass into energy every single second. Not burns, not consumes in a chemical sense, converts. The matter ceases to exist as matter. It becomes photons, neutrinos, kinetic energy, radiation spreading outward through the solar interior. The sunlight that hits your face on a clear day, that warmth, is matter that no longer exists. It was once hydrogen. Now it's light. You are being touched by the ghost of mass. But here's the part of the story that most explanations skip entirely. And it's the part that, when I first worked through it carefully, made me stop and reconsider what I thought I understood. The sun's core is extraordinarily hot. 15 million degrees Celsius is a temperature that is difficult to even conceptualize. And yet, by classical physics, it is not hot enough for fusion to happen. The protons moving around in the solar core have thermal velocities determined by that temperature. Those velocities give them kinetic energy. But when two protons approach each other, they're both positively charged, and like charges repel. The electromagnetic repulsion between two protons creates an energy barrier, the Coulomb barrier, and the protons in the Sun's core simply don't have enough kinetic energy to climb over it. Classically, the Sun doesn't work. What actually happens is quantum mechanics, specifically quantum tunneling. In quantum mechanics, a particle doesn't have a single definite position or a single definite trajectory. It has a wave function, a probability distribution spread over space. And this means that even when a proton classically doesn't have enough energy to get past a barrier, there's a small but non-zero probability that it will be found on the other side anyway. It tunnels through, not over, through. The Sun runs on a quantum loophole. Without quantum tunneling, the electromagnetic repulsion between protons would be insurmountable at solar core temperatures. Fusion wouldn't happen. The Sun would not shine. There would be no solar system, no Earth, no life. The warmth on your face right now exists because quantum mechanics permits particles to be somewhere that classical physics forbids. Every photon from the Sun is a consequence of something that, by the laws of 19th century physics, couldn't happen. Now, how often does tunneling occur? How fast does fusion run? This is the part that surprises almost everyone. It's extraordinarily slow. In the proton-proton chain, the dominant fusion pathway in stars like the Sun, the first step is the fusion of two protons into a deuterium nucleus. This requires one of the protons to convert into a neutron via the weak nuclear force simultaneously with the tunneling event. The weak force is, as its name suggests, weak. The probability of this happening for any given pair of protons in any given encounter is vanishingly small. A typical proton in the Sun's core might wait on the order of 1 billion years before it successfully fuses. The Sun is not a bomb in slow motion. It's a barely controlled trickle, a fusion rate so low that the reaction is almost running at idle. The Sun produces about 276 watts of power per cubic meter of core volume. For comparison, your body produces roughly the same power density through metabolism. The Sun shines not because it's fusing rapidly, but because it's enormous. The sheer volume of the core compensates for the glacial pace of individual reactions. And this slowness is not a flaw. It is the reason we exist. If the proton-proton chain were faster, if tunneling were more probable, or the weak force were stronger, the Sun would have burned through its hydrogen in millions of years, not billions. Life on Earth needed roughly 4 billion years to go from simple chemistry to complex organisms. That time was available because the Sun burns slowly, because quantum tunneling is rare, because the weak force is weak. The improbability of fusion is, in a very direct sense, the reason biological complexity had time to emerge. We owe our existence to a quantum event that happens once per proton per billion years. Now, the energy is released in the core, but how does it get to you? A photon produced by a fusion event in the Sun's core doesn't travel straight outward. The solar interior is extraordinarily dense, plasma so tightly packed that a photon travels only about a centimeter before being absorbed and re-emitted in a random direction. This happens over and over. The photon doesn't travel, it wanders. a random walk through the solar interior, absorbed and re-emitted trillions of times, each step in an arbitrary direction. The average time for energy to diffuse from the core to the surface, from photon creation to the moment it leaves the Sun, is estimated between 10,000 and 100,000 years. The uncertainty reflects how difficult this calculation is, but the scale is not in doubt. It is not seconds, it is not years. It's geological time spent wandering through plasma. Then, once it reaches the surface, it crosses 150 million kilometers of vacuum in 8 minutes. The sunlight warming you right now was generated in the solar core before Homo sapiens existed as a species. That energy was produced, wandered through the sun for tens of thousands of years, crossed the void in 8 minutes, and arrived at your skin today. You are the destination of an extraordinarily long journey. Step back now and look at the whole picture. What is the sun actually doing? At the largest scale, it's doing one thing: trading mass for time. It started with a reservoir of hydrogen, the raw fuel from the Big Bang, concentrated by gravity into a star. It's spending that hydrogen, converting a fraction of its mass into radiation with every second that passes. 4 million tons per second, every second, for 4.6 billion years, with another roughly 5 billion years remaining. When the core hydrogen is exhausted, the story changes. The core contracts, heats further, and the sun expands into a red giant, fusing helium, then carbon, restructuring and renegotiating with gravity at each stage. Eventually, it sheds its outer layers and leaves a white dwarf, the dense, cooling remnant of what was once a star. The whole biography, ignition, main sequence, giant, remnant, is written in E=mc² and gravity. The sun is a slow, magnificent act of self-consumption, sustained by quantum mechanics, initiated by gravity, carrying energy that traces all the way back to the hydrogen produced in the first minutes of the universe. I want to be honest about what we don't know, because I think it matters. The standard solar model is one of the most successful quantitative models in all of astrophysics. Solar neutrino flux measurements, once a famous discrepancy, now resolved by neutrino oscillation physics, confirm our understanding of the core. Helioseismology, using acoustic waves in the sun as a probe of its interior, has given us a detailed picture of the solar structure. Our understanding of the sun is deep and quantitatively precise. And yet, the solar corona, the sun's outer atmosphere, is millions of degrees hotter than the surface below it. Heat flowing from cooler to hotter regions violates naive thermodynamic intuition, and despite decades of research, the precise mechanism of coronal heating is still debated. Several candidates exist: magnetic wave heating, nano-flare reconnection events, others. The Sun is closer to us than any other star, the most studied object in astronomy, and this basic feature of its atmosphere remains an open problem. We understand the Sun better than almost anything else in the cosmos. We don't understand it completely. And now I want to close with something that I think earns the right to be said, because we've actually done the work to get here. Every calorie of energy in your body has a traceable history. It came from food. The food came from organisms that, directly or indirectly, captured sunlight through photosynthesis. The sunlight came from fusion. The fusion came from gravitational collapse. The gravitational collapse came from a hydrogen cloud. The hydrogen came from the Big Bang. The energy running your brain right now, the electrochemical signals, the metabolic heat, the motion of your eyes across this screen, is converted mass. It was once hydrogen in the early universe. It collapsed into a star. It fused. It wandered for 100,000 years through plasma. It crossed the void. It was captured by a leaf, stored in a sugar molecule, eaten, digested, metabolized, and now it's a thought. You are not merely warmed by the sun, you are organized sunlight. The carbon in your body was forged in stars that died before the sun was born. The energy running you is fusion output, ancient and redirected. You are the sun's mass, in one of its stranger configurations, one that looks back at the sun and asks where the light came from. That question, the one you're asking right now, is the universe examining itself. And the answer, when you follow it all the way, is that you and the sun are made of the same story, just told at different speeds. I find that worth knowing.